Good evening, everyone. My name is Devlina Maiti. I am a research scholar in the Department of Mathematics, IIT Kharagpur, and I am also an NPTEL TA for the course Real Analysis 2, and this is the third problem solving session for this course. So we'll wait for 5 minutes, then we'll start this session. Okay, so let's start this session. So, am I audible?
Yes, ma'am.
Okay. So in the last session we have discussed about completeness and compactness, right? So in the last session we have done this problem where we see that CAB, the function space, that is the class of all continuous functions defined in AB, right? So this space with this metric where D was defined by FG by supremum of Ft minus Gt, right? So we have seen that CAB with this metric was complete, right? So in the first problem we will see that CAB with this metric, suppose it was D1 and now it is D, where D is defined by, this is Fg equals to right. So CAB with this metric is not complete. Right. So first we will prove this. So it means there is a Cauchy sequence which does not converge, right? So we'll choose this Cauchy sequence xmt, which is 0 if in 0 to half and 1 if half plus 1 by m to 1. Okay. So this is a sequence in CAB. So this sequence, how does it look like? So suppose this is our arc, this is 0 1, right? So from 0 to half it is 0, there is somewhere half, and it is suppose half plus 1 by n, right? So here is our 1. So the graph of this xm is, so first from 0 to half it is 0 and half plus 1 by m to 1 it is 1, and from half to half plus 1 by m it is actually this m into x minus half, it is actually the line segment joining these two. If you find out the line segment joining this half 0 and half plus 1 by m to 1, we will get y equals to m into x minus half. Okay, so this is the line segment. Okay, so this is xm, so this is xm, right? So first it will be Cauchy. Why? Because if you take xm for m not equals to n, so it will be somewhere here. So xm will be this one will be xn, right? So if m not equals to n, then this is xn and this is xm, right? These two continuous lines. So dxm, so what is dxm xn? So it has to be Cauchy. So dxm xn must go to 0 as mn goes to infinity, right? Now what is dxm xn? It is integration of 0 to 1 mod xmt minus xnt, right? So from the graph we can say that this difference is nothing but here from 0 to half both are same, and it is half plus m, and this one is half plus 1 by n, right? So this integration is nothing but the area of this region. Okay. Area of this region. So this difference dxm xn is nothing but this area of this region, and as mn goes to infinity, these two are going to be close, so the area goes to 0, right? So that's why dxm xn goes to 0 as mn goes to infinity. So xm is Cauchy. Now we will show that xm converges to a function which is not continuous. Then we can tell that this CAB is not complete because it is a collection of continuous function, and xn converges to a function which is not continuous, so it can be complete, right? So now for every function x belongs to this CAB, the difference between xm and x is 0 to 1 mod xmt minus xt, right? And if we break the integration from 0 to half xm is 0, so it is only xt, and then half to, let am be this number 1 half plus 1 by m. Okay, so half to am, it is xmt minus xt, and from am to 1 xm is 1, so it is 1 minus xt, right? Now if xn this xm converges to x, then dxm xn goes to 0 as m goes to infinity, right? Now dxmx goes to 0 means each of this integration goes to 0, right? So this implies each integral in the above goes to 0 as m goes to infinity, right? Now we see that each goes to 0 means what? So from the first one, so each goes to 0, so xm this x is going to be 0 on 0 from 0 to half, right? So how does x looks like? So xt must be 0 if 0 less equals to half, less equals to x, t less equals to less than half, from 0 to open half. So what we are trying to show that each of this integral goes to 0. So this x must go to 0 in 0 to half, and from the last one, from am to 1, right? As m goes to infinity, this am goes to half as m goes to infinity. So from half to 1 xt, from the last integral, we can say that when m goes to infinity, am goes to half, so this integral has to be 0, so xt must be 1 from half to 1 in the limiting case. So when m goes to infinity, so in half to 1, open half to 1, it has to be 1 from the last one, right? So we see that this function is what? This function is from 0 to 1, so it is 0 from 0, it is 0, and then from half to 1 it is 1, open. This is open, right? So this xt, you can define anything at the point half, but still it can never be continuous, right? So this xt is not continuous in 0 1, right? Oh, I think I have written AB, so it is actually 0 1. Now it can define for any AB, like in this manner. Okay, so we see that if xm goes to a function x, any function, then that function will not be continuous. So this Cauchy sequence xm does not have a convergent subsequence, or it does not converge, right? So C01 with this metric is not complete, right? So now we'll start with connectedness. So we'll define now we'll discuss about connectedness and components. Okay, so first the definition. So first we will give the definition of separated set. So what is a separated set? Now two subsets A and B of a metric space xt are said to be separated if A intersection B bar equals to B intersection A bar equals to phi. Okay. So this means what? This means A intersection B bar is phi. This means A does not contain any limit point of B, and same is for this case B intersection A bar, right? So this means no point of A lies in the closure of B and no point of B lies in the closure of A, right? So this means in the closure of B, and same thing, and no point of B lies in the closure of A, right? So A does not contain any limit point of B and B does not contain any limit point of A, then they are called separated set. Okay, now we'll say a set E subset of X is said to be connected if E is not a union of two non-empty separated sets. So E is said to be connected if E is not union of two, that is E cannot be written as union of two separated sets, non-empty separated sets, then E is connected, right? So now here notice, now separated set is always disjoint, right? But disjoint set may not be separated. So this note is that separated sets are disjoint. Need not be separated. Right? So we have to give an example. So if we take A to B, half this interval 1 to 2, and B is suppose 0 1. Okay. So A and B are disjoint, right? So because A intersection B is 5. Now A bar intersection B is what? This singleton set 1, and similarly B bar intersection A, it is 5. But A bar intersection B is singleton 1. Okay. So this means A, B are not separated. But they are disjoint. Right? Now there is another definition of connectedness where they said that if E is said to be connected if E is not union of two non-empty open sets. Okay, open sets or non-empty closed sets. These two definitions are same. You can prove these two definitions are same means it can follow from another. If we take this is to be the definition, then you can see that that definition follows from this one. Okay, so the first result is a metric space. So this is a characterization of connected sets. So a metric space XT is connected if and only if any of the following holds. Okay, so the first one is the only subsets of X both open and closed are X and phi. So phi and X are the only open and closed subsets of X. And the second one is every continuous function from this metric space X to this set Y, which is the set of these two numbers 0 and 1, is constant. Okay, so we prove this result. So first we will prove the first one. So this is a if and only if condition. So suppose X is connected. X is first one. X is connected. Then the only subsets of X which are both open and closed are X and phi. Okay. So we prove this by negation. Okay, so if X is disconnected, then what? So X is disconnected means we can write X as a union of two non-empty open set, right? So then X equals to some A union B, where A, B are non-empty open subsets of X, right? Oh sorry, this is non-empty disjoint open subsets. Empty. Oh, sorry. Disjoint open subsets of X. Then X is disconnected, right? So now A is what? A is X minus B, right? So B is open, so X minus B is closed. So A was open and now we have proved that A is closed. So we have found a set, non-empty set, which is both open and closed, right? We have chosen X to be disconnected, and we have found a subset, non-empty subset, which is both closed and open, right? So the first one is proved. This means what? This means if A happens, then X is connected, right? This is the proof by negation, and we will prove the converse part. So for converse, so let E, which is not phi, not X, be a subset of X which is both open and closed. Right. Now for the converse part, we have chosen a set E which is both open and closed, and which is non-empty, which is not phi and X, right? Not trivial. So we'll prove that X is disconnected, right? So E is open and closed. So now since E is open, so E complement is closed, right? Or we can say E, since E is closed, E complement is open, right? Now X can be written as E union E X minus E, which is E complement, right? And E is open, E complement is open, and both are disjoint. So we have written X as a union of two non-empty disjoint open subsets of X. So X is disconnected. X is non-empty because E is non-empty because we have taken E not equals to phi. So X is disconnected. Right? Now we'll prove the second one, B. It is done. So for B, so suppose it will also, we will prove this by negation. So first we will choose X to be disconnected. So for B, so let X be disconnected. So X equals to A union B, where A, B are same ABR non-empty disjoint open subsets of X. Right. Now we have to show that X, we have taken X to be disconnected. So there will be negation of this comment B. Right. This means there exists a continuous function which is not constant. Right. That we will see. So we will define a mapping, define f from x to this y which is 0 1 by, we are defining this map by fx is 0 if x belongs to A and 1 if x belongs to B. Right. So first we will prove that f is continuous. Right. Now since A intersection B is phi and AB are disjoint and A union B is the whole space X, so this function is well defined. So f is well defined. It is defined at all points. So f is well defined. Now also f is an onto mapping, right? Because for f inverse 0 there are points and for 1 there exists f inverse 1, there is some point, right? Because A, B are non-empty. So f is also onto, means surjective. So f is a surjective map. We'll need this property of f later. So f is surjective, right? Now what is now we have to prove f is continuous, right? Now we know that f is continuous if and only if inverse of every open set is open, right? This is a characterization of continuous function or open sets. So since there are only two elements in the codomain, so we can find this f inverse 0. So f inverse 0 is what? A. What are all the open sets of Y? So open sets of Y are what? Open sets of 0 1 are nothing but 0 singleton 0 singleton 1 0 1 and phi, right? These are the only open sets of 0 1. This is a discrete set. So we will find inverse of all these open sets. So f inverse 0 is 1, f inverse 1 is B, f inverse phi is phi, and f inverse y, which is 0 1, is x. Right? Now A is open, B is open, phi is open, and x is also open. Right? So this implies f is continuous. Right? Inverse of every open set is open. So we have proved f is continuous and we see that f is not constant. So this is our negation, right? So we have chosen x to be disconnected and we found that there exists a continuous function which is not constant, right? So one part is done. Now for the converse, now it says every continuous function is constant. So suppose there exists a continuous, so suppose there exists a continuous surjection f from x to y, right? So it is not constant mean it has to be surjective, right? Constant mean it has to be only 0 or only 1. So it is not constant means there are points in the inverse of f inverse 0 or f inverse 1. So f takes both the values 0 and 1. Then f is not constant. So suppose there exists a continuous function which is not constant. That means there exists a continuous onto mapping from x to 0 1. Right. Now since it is onto and f is continuous, right? So f inverse 0 is open and both f inverse 0 and f inverse 1 both are open, right? Are open as f is continuous and singleton 0 and singleton 1 are open in y. So f inverse 0 and f inverse 1 are open in x, right? Now they are open in x and we can say that they are disjoint, right? Because if they are not disjoint, there are some points in common, then both that point will go to 0 and 1. So it does not make any sense, right? So they are disjoint also. So f inverse 0 and f inverse 1 are disjoint, right? Because if there is some point belongs to this 2, it means what? It means if a is 0 and if a is also 1, so it is not valid, right? So it is not true. So they are disjoint. So they are disjoint and x is equals to f inverse 0 union f inverse 1, right? Because it was onto and they are disjoint, so x is union of these two. So we have written x as a union of two non-empty open subsets. So x is disconnected. Right? So B is also true. So B is also true. Now take this for problem 1. So suppose X is the discrete metric space. So xt is the discrete metric space. Then any set A, then any set A with at least 2 points is disconnected. Right? Why? So suppose A is any set with at least 2 points, right? And let X belongs to A. So A can be written as x union A minus x, right? Now for discrete metric space, singletons are open, so this is open. Singletons means any subset of this set is open for discrete metric space, so this is also open. And this is non-empty because A contains at least 2 points, so both are non-empty disjoint open subsets, right? So we have written A as a union of two disjoint open subsets of A, so A is disconnected, right? So any set A with at least 2 points is disconnected in discrete metric space, right? And for 2, we'll take the set of rationals Q with the subspace metric of the usual metric is not connected. So Q with the subspace metric is actually the discrete metric space, right? Here also singletons are opens. You can prove it another way. So we have to find that Q can be written as union of two open subset, disjoint open subset or closed subset, right? So we'll take this. So this is our R, right? So root 2 is belongs to R minus Q, right? This is irrational number. So this set A, which is this interval minus infinity to root 2 intersection Q. So this is also open, right? Because open sets of Q is nothing but open sets of R intersection Q, right? So A is open. Similarly B, which is from root 2 infinity to Q, this is also open, right? So A, B are open in Q, and they are also disjoint, right? From minus infinity to root 2 and root 2 to infinity, we are taking all the rationals, so they are open and they are disjoint, and Q equals to A union B, right? So we have found a separation of Q, non-empty separation. So A, B are non-empty disjoint subsets of Q, and Q equals to A union B. So Q is not connected. Here the important thing is this A and B are also closed. Why? Because A was what? A is minus infinity root 2 intersection Q, and this is the same thing as minus infinity closed root 2 intersection Q, because Q root 2 is a irrational number. So if I take open root 2 or closed root 2, both are same. So this is open in R and this is closed in R. So this implies A is both open and closed in Q, right? So open and closed sets of a subspace is nothing but intersection of that subspace with any open or closed sets of the original space, right? So this is a note actually. Also we can see that the only connected subspaces of Q are one point set, that is the singletons. So also connected subspaces of Q are the one point sets, that is the singletons. Why? So this is so suppose it A is a subset which contains at least 2 points. So choose so let Y be a subspace of Q containing points P and Q, where P is less than Q, means they are not equal, right? So choose A belongs to A, an irrational number such that P less than A less than Q, right? So A lies between P and Q. Then this set A, which is Y intersection, in a similar manner, minus infinity to A, and B equals to Y intersection A infinity, right? Then Y equals to A union B, right? And A, B are non-empty because P belongs to A and Q belongs to B. So both are non-empty and they are open. So Y is disconnected. So any subspace which contains more than one point are not connected. So Y equals to A union B and AB are disjoint, non-empty, open subsets of Y, right? So Y is disconnected, right? So we have proved this one. Okay, so let's look at another problem. So consider this set capital X, which is the set of these tuples, two tuples with Y equals to 0 union xy, where x greater than 0, y equals to 1 by x. So the first one is A, suppose, and the second one is B, right? So what is the graph of these two sets? So the first one says all those xy where y is 0, it means the real line. So it is A. So this is A. And B is what? B is all those xy where xy equals to 1 and x is greater than 0. So it is nothing but this set, this graph. This B will never touch A, okay, because in A y is 0, and for the class for this set B y can be close to 0 when x goes to infinity, but it is not actually 0, it is asymptotic, right? And also these two sets A B are closed in R2, right? They are lines, kind of curves, so they are closed because if we take the complement of this, then you can say that the complement is open. You can prove that. So AB here AB are closed, right? And we have written X to be A union B. So to prove X is disconnected, this set is actually X is disconnected. Okay. To prove X is disconnected, we have to show A and B are separated, right? So neither of them contains a limit point of the other one, right? That is the definition of separated set. A bar intersection B and B bar intersection A is 5, right? Now here A and B both are disjoint and they are closed. So A bar equals to A and B bar equals to B. So A bar intersection B is B bar intersection A, which is nothing but A intersection B is 5. And they are non-empty, so X is disconnected. Right? Okay. So let's go to the another result, which is a theorem. So maybe 2. Right. So let A be a connected subspace of X. Now if A is a subset, B is a subset of A bar, then B is also connected. Okay. So this means if B is formed by adjoining to the connected subspace A, some and or all the limit points of A, then B is connected. Okay. So if we add A with some of its limit point or all the limit points of A, then B is also connected. So in other words, it says if B is formed by adjoining to the connected set A, some or all of its limit points, then B is connected. Right. So every set between A and A bar is connected. Right? So we'll look at the proof. Okay, so for proof, so A is connected. A is connected and A subset of B subset of A bar. So on the contrary, so suppose B is disconnected. So suppose B is disconnected means B equals to some C union D. So C union D, where C, D are separation. So C, D are non-empty, or I can write C, D is a separation of B. Right. So it means C, D are non-empty subsets of V. Right. So we have proved this theorem actually, where it says if a connected set is okay, I think I have not proved this result, right? Okay, so this theorem needs a lemma. So we'll first prove that lemma. Okay. So this is lemma 1. It says a connected set in a metric space which is contained in the union of two separated set is contained in one of them. So this actually means if A is connected and or suppose C is connected and C is a subset of A union B, where A, B are separated set. This means A, B are non-empty, sets, and A bar intersection B equals to B bar intersection A is 5. Right. Then it says C is contained in either A or B. Right. If a connected set is contained in union of two separated sets, then it must be contained in one of them. So the proof is easy. So just put G equals to C intersection A and H equals to C intersection B. Right. Then C equals to what? C is a subset of A union B. So C equals to C intersection A union B. So it is nothing but C intersection A union C intersection B, and it is nothing but G union H, right? And since GH are non-empty, okay, no, not non-empty. So since C is connected and we have written C to be union of these two sets, right? So GH is a separation of C, and since C is connected, one of them must be phi, right? If both of them are non-empty, then it will imply C is not connected, right? So since C is connected, one of them has to be, or both of them must be non-empty, empty, right? So since C is connected, one of G and H is phi, right? Both of them cannot be phi because then C will be phi, right? So if G is phi, then what? Then G C equals to, C is contained in B, right? Then C equals to H, and H is what? H is C intersection B. So it implies C is contained in B. And if H is phi, then C is G, which is C intersection A. So C is contained in A. So we have proved if a connected set is contained in a union of two separated sets, then it must be contained in one of them, right? Now we'll prove this theorem. So B is a set in between A and A bar, where A is connected, and we'll show that B is also connected, right? So proof of, now this is proof of theorem 2. Yes, theorem 2. So let A be connected and A subset of B subset of A bar. Suppose B equals to C union D is a separation of B, right? So now A is a subset of B, which is C union D. So A is contained in union of two separated sets, right? And A is connected. So A must be contained in one of them by lemma 1, right? So by lemma 1, A is entirely contained in C or in D, right? So suppose A is contained in C, right? So A is contained in C means A bar is contained in C bar, okay? So B is a subset of A bar, so this implies B is a subset of C bar, right? So we have written here this line, C, B equals to C union D is a separation, right? C union D is a separation means C bar intersection D equals to C intersection D bar equals to 5. Right? So C bar and D both are disjoint. And B is contained in C bar. We have found that B is contained in C bar. So B does not intersect D. Right? C bar and D are disjoint and B is contained in C bar. So this means B cannot intersect D. Right? So B cannot intersect D means D is 5. Right? So this is a contradiction because D was non-empty. This is separation means both are non-empty. C and D both are non-empty and this satisfies this condition. So this implies D equals to 5, which is a contradiction. Right? Because there C, D are non-empty. Right? So this is a contradiction. So every set in between A and A bar are connected. Right? So we have proved theorem 2. Right? Now so I will not prove these theorems now because it takes so much time. So this second theorem is image of a connected set under a continuous mapping is connected. Okay, so I am not proving this theorem for time. This time is very short, so you will try this. Okay, you can find it in any book also, but first you can try on your own. Okay, this is easy. So image of every connected set under a continuous map is connected. Okay, so we'll use these theorems for problems. Okay, so now we'll define this definition of path connectedness. So what is a path? So suppose x and y are 2 points in x. So how can we define the path between x and y? There can be many paths, but how can you characterize this path? So suppose x and y are given. Suppose given points x and y in the space x. So a path from x to y is a continuous mapping. So any path can be characterized by continuous mapping. So a path from x to y is a continuous map. Say f from AB to x. You can take 0 1, close 0 1 to x or any AB to x. Of some closed interval in R to x such that the starting point, that is fa, is small x and the end point fb is y, right? So this is suppose x, this is y, and this is the path, right? So this path is nothing but image of this closed set AB F, right? So this x is FA and y is FB. Right? So any path can be characterized by a continuous mapping from a closed interval to that image, that path, right? Like suppose this is our circle, right? This x square plus y square equals to 1, right? So it is also a path from, this is 0, this is minus 1. It's a closed curve, right? Now we can define a mapping from 0, 1 to this curve. What is this mapping? So t, ft is actually e to the power 2 pi it, or we can take e to the power it, right? Where t belongs to, since I am taking 0, 1, I have put 2 pi. So this circle is a path, or it is a closed curve, right? So f0 is nothing but 1 and f1, which is also f1 is e to the power 2 pi I, this is also 1, right? And f half is e to the power I pi, which is minus 1, right? So this e to the ft equals to e to the power 2 pi it, it gives a path from 0 to minus 1, or maybe minus 1 to 0, any 2 points in the circle, right? This 0, 1 goes to this circle, this is a closed circle. So any path, continuous curve or a path can be characterized by continuous mapping from a closed interval of R, right? So now we will define path connectedness. So you have defined a path, now a space. So a space X is said to be path connected if every pair of points of X can be joined by a path. By a path in X, right? So X is said to be path connected if every pair of points of X can be joined by a path in X. Okay. So this means path connected always imply connectedness, right? But we will prove this. So path connected imply connected. How? So let X be, X is path connected. Right. Now we'll prove that X is connected. So suppose X is not connected. So suppose X has a separation. X equals to A union B is a separation. Means AB are non-empty disjoint subsets of X. Right? Now mm, choose any path in X. So let f from this closed interval AB to X be any path. Right. Now since we have taken that X has a separation, means X is disconnected, so there must be some contradiction, right? So let f is any path, and since AB connected, right, and f continuous, right? So by this theorem 3, image of any connected set is connected. So FAB is connected in X, right? So FAB is connected, and FAB is contained in A union B, because A union B is the whole set X, right? So FAB is contained in A union B. So a connected set is contained in separated set, means it is contained in either A or B. It must be contained in one of them, right? By theorem, I think by lemma 1 maybe. Yes, by lemma 1, if a connected set is contained in union of two separated set, then it is contained in one of them. So this line we get from by theorem 3, right? And by lemma 1, f of AB is contained in A, or f of AB is contained in B, right? So this means any path in X is either contained in A or either contained in B, right? So the paths from A to B is not there, right? So X does not contain the paths joining the points of A and B. So this means X is not path connected. Path connected means for every pair of points there must be a path in X, right? So this is suppose this is A, this is B, and every path lies either in A or either in B, right? So the paths joining the points of, suppose in X and in Y, X belongs to A and Y belongs to B. So the paths joining this AB, they are not there, right? So this contradicts that X is path connected. So this means, so there is no path in X joining the points, joining a point of A to point of joining a point of A to a point of B, right? So this contradicts that X is path connected, because path connected means for every pair there must be a path in X joining that point, right? So we have chosen X is disconnected and we found a contradiction. So this means X is connected. So path connected always imply connectedness, but the converse is not true. So we'll see an example that the converse is not true. So converse is not true. So for that we will take this set. So let S denote the subset of R2 is equals to X sine 1 by X. So this is a classical example which is connected but not path connected. So this set, okay, so how does this look like? So the function is what? The function is sine 1 by x, right? So if we take this function from R to R2, which x goes to x sine 1 by x, right? So this f is continuous in open 0 to close 1, right? So f is actually continuous on open 0 closed 1, and the map of f is something like this. So this is suppose 1 and it is minus 1. So this is a sine function, so it oscillates, and since at the point 0 it has a pole something like that. So at x goes to, when x goes close to the 0, this function is not defined actually at 0, right? So near 0 it oscillates infinitely many times. So near 0 it oscillates infinitely many times, but it never touches the line minus 1 to 1. Okay, so this is the graph of this function x sine 1 by x. This is sine 1 by x. Okay. Now, what is S bar? So since it oscillates infinitely many times in near 0, we'll see that S bar will be S union this interval minus 1 to 1. Since it oscillates infinitely many times close to 0, S will be S union this set. This set is what? 0, y, where y lies between minus 1 to 1. Right, this is S bar. Okay. So F is continuous mapping on 0, 1. Right, so this is the image. So F of 0, 1 is actually S, and this 0, 1 is connected, 0 closed 1, open 0 closed 1 is connected, F is continuous, so connected set under a image, under a continuous mapping is also connected. So S is connected by theorem 3, I think. Right? So S is connected, and we have seen that a set A, any set B from a connected set A to A bar is connected, right? We have seen in theorem 2, right? Since now S is connected, so S bar to S bar up to S bar every set is connected. So S bar is also connected. So by theorem 2, S bar is also connected, right? Now we prove that S bar is not path connected. Okay. Now to show, we prove that S bar is not path connected. So there must be 2 points in S bar such that there is no path joining the 2 points, right? So we'll see that if we take a point in -1 to 1 and any point in S, then we cannot find a path joining that points. Okay, so suppose there is a path. So suppose there is a path if from a closed interval AC, which is a subset of 0, 1 to S bar. Beginning at 0 and ending at a point of S. Right. So it starts from 0 and joins some points in S. Okay. So then we'll find some contradiction, right? So this is our map. So this is -1 to 1. So this is 0, here 0, and here is suppose some point. So I'm saying is that there exists a path joining 0 and that point, some point of S, right? Now define this set E, which is all those T in 0, 1, open 0, 1, or we can take close 0, 1 such that Ft belongs to 0 -1 to 1, right? Means for this path F, all the points in this line -1 to 1, which maps for all those T which maps to this line, we are taking that set, called this set to be E, right? F is a mapping from this 0, 1, this 0, 1 to here, right? Sin 1 by x, by sin 1 by x, right? Now all those T in 0, 1 for which the value Ft belongs to this -1 to 1 on the blue line, -1 to 1, we are collecting all those T and we are naming this by E, capital E, right? So this E is what? E is F inverse of this set, this 0, -1, 1, right? And this 0, -1, 1 means this line -1 to 1 in R2 is closed, so E is also closed, right? So E is closed and E is also bounded. E is a subset of what? 0, 1, right? So is closed and bounded, so it is compact, means E contains the largest element, right? E is bounded, so E, there must be some largest element in E, right? So E has a, so E has a largest elements, say B, right? This means what? This means B is the final exit point from this -1 to 1. Okay. So then if now we can say BC, F was a mapping from AC, closed interval AC to S bar, right? Now there must be some points, repeated points which belongs to this line -1 to 1, right? Means there must be some ft1, ft2, like this ftn, which belongs to this 0, -1, this blue line in this graph, right? Now we are choosing a B to be the largest one, right? So a B is the largest one. So after B, all the values must be in S, not in 0 to 0 -1 to 1, because we have chosen B to be the largest one, right? So since B is the largest one, so then B is the largest in T1, T2, like this, right? So since B is the largest one, this, if we restrict B, F from BC to R, BC to S bar, then this is a path that maps B to this vertical segment, this vertical blue line, 0, -1, 1, and all the other points to S, and maps other points of this BC, means open B to close C, to S, right? So this implies, for convenience I am saying that, suppose so choose BC 0, 1. For example, I am saying, so let ft is what? Ft is in R2, so it is xt yt. So I am saying FB is in -1 to 1, so then x0 is what? x0 is 0 because it's belong to B, here is 0, so it is 0, xt is 0, and all the xt's are greater than 0, right? And yt is nothing but 1 sine 1 by xt. This is the mapping, x sine 1 by x. So x valid from 0 to 1, so x0 is 0 and yt is sine 1 by xt, where t is greater than 0, right? Now you can choose Tn to be 2 by 2n plus 1 pi. Then we will see that Tn goes to 0 as n goes to infinity. Right? But ytn, okay, also you can take xtn to be, maybe xtn to be 2 by 2n plus 1 pi, right? then xtn goes to 0 and ytn will be minus 1 to the power n, right? So we have found a sequence such that this xtn goes to 0 but ytn, the curve sine 1 by xt, does not go to 0, does not converge, right? It is a minus 1 to the power 1. It is oscillating, so it never converges, right? So f is not continuous, right? So if this implies ytn does not converge, this sequence converge. So this is a contradiction. That f is continuous, because in continuous, if xn goes to x, then fxn goes to fx, if and only if condition, right? So this is a contradiction. This means it is not connected, not path connected, right? So S bar is path connected, but it is not path connected. So this is a classical example. Okay, so let's look at another examples, another problem. So problem 1 says, so let f from S1 to R be a continuous function. Okay. So show that this S1 is the circle mod z equals to x square plus y square equals to 1. Okay. So show that x belongs to S1. There exists a point x belongs to S1 such that fx equals to f of minus x. Okay. So S1 is this x square plus y square, this circle, unit circle. So we'll prove this problem. So take this function gt, which is f of e to the power 2 pi I t minus f of minus e to the power 2 pi I t. So this e to the power t goes to e to the power 2 pi I t, it means it goes from 0 1 to the unit circle, right? We have already seen that. So all these points of the circle mod z equal circle, unit circle, can be parameterized by e to the power 2 pi I t, right? You have already seen that. So this where t belongs to what? T belongs to 0 1, right? So actually this S1 we can also write in this form, e to the power 2 pi I t, where t belongs to 0 1. Right? This is the set S1, the circle, unit circle. And these t's are nothing but e to the power I 2 pi I t. This is the angle, this denotes the angle, right? E to the power I theta means theta is the argument. So here the angles are what? Angles are 2 pi t, and t runs from 0 to 1, so the maximum angle can be 2 pi, This is a parameterization of the unit circle. Okay. So we have taken this function gt equals to this. So we have to prove that fx, there must be some x such that fx equals to f of minus x. So there must be some t in 0 1 such that gt is 0, right? Then f of e to the power it equals to f of minus e to the power 2 pi it. So we can find a point x in the point x in unit circle if we can find a t in 0 1. This is the same thing, right? So we have to show that gt equals to 0 for some t. This is our goal. So since f is continuous, f is continuous, so g is also continuous. G is composition of this f and e to the power 2 pi it. So both are continuous. So g is also continuous. So continuous on 0 1. Right. Now g minus t is what? G minus t is f of e to the power 2 pi it minus f of e to the power 2 pi it, right? Now e to the power minus something can be written as, or it is actually f of minus e to the power 2 pi it, because e to the power I pi is 1 minus 1. Okay. So e to the power I pi into e to the power 2 pi it will be e to the power I into also we can take this gx to be fx minus f of minus x, right? Then it will be easier to show. So take gx to be fx minus f of minus x, where x belongs to now S1, the circle. So then g of minus x will be f of x, which is nothing but minus of gx, right? This means, and g is continuous, so, and S1 is connected. S1 is connected. So GS1 is connected, right? So GS1 is what? It is a function from G is a function from S1 to R, right? So GS1 is connected in R. So it must be an interval, right? And we see that G, if G of x is greater than 0, then G of minus x will be less than 0, because G of minus x is minus of gx, right? So GS1 is connected, and if some A is greater than A belongs to GS1 and A is greater than 0, then minus A also belongs to GS1, right? Because if gx is 0, G minus x is minus of gx, which is less than 0 and which also belongs to GS1. So this means GS1 has to be in this form, right? Because GS1 is connected, and for every A greater than 0, there is a minus A belongs to GS1, right? So GS1, and since this S1 is connected compact set, right? So it with an image of every compact set under a continuous mapping is also compact. So GS1 is a connected compact set of R. So it has to be in this from minus A to A, right? So you see that since GS1 is this set, so 0 belongs to GS1. So 0 belongs to GS1 means there exists some x0 belongs to S1 such that Gx0 is 0. So Gx0 is 0 means fx0 equals to f of minus x0, right? So we have found a x0 for which f of x0 is minus f. So we have proved this problem. Okay, so since this is at time, so I will take this is the last problem now. So this says, show that if A is a countable subset of R, subset of R2, then if we remove this A from R2, then it remains path connected. R2 minus A is path connected. Not only connected, it will be path connected. Okay. So how? So A is countable, so we can enumerate this A. So suppose A is A1, A1, A2, A3, like this. Right. A is connected and A is a subset of R2. Right. So this is our R2 and this is A1, A2, A3 and so on. Right. So we have to show that R2 minus A is path connected. So you have to take 2 points from R2 minus A and you have to prove that there exists a path joining X that points which lies in R2 minus A. Right. So take xy belongs to R2 minus A. So this is suppose x, and here is some our y, right, these 2 points. So if x and y are equal, then this is trivial, this is a constant path. So if x equals to y, this is trivial, this is a constant path, right, constant mapping. So suppose x not equals to 1. Okay. So now we have to find a path from x to y in R2 minus a. Right? Oh sorry, this is R2. So now consider all the lines through x. Right? All the lines through x. So this is x. So all the lines I am considering. Right? And similarly for y. So there are infinitely, uncountably many such lines, right? So now consider all the lines from x, right? So they are uncountable, so there is uncountably many lines through x, right? And now for each n belongs to this a, now joining x, this x, and suppose a2, there is only exactly one card, not exactly one, exactly one line, right? So there are infinitely many paths, but line is only one. So for each n belongs to a, there is exactly one line from x to a, right? So from x to a, capital A, there are countably many lines because a is countable. So from x to a, therefore from x, there are only countably many lines from x to capital A, right? Similarly from y to capital A. So from x to capital A, there are countably many lines, and y to capital A, there are countably many lines. Now if we remove all these lines, all these countable lines, so the left are also uncountable, so uncountably many lines are left if we remove all this type of lines, right? So if we remove all these lines, all these countably many lines, right? Many lines from R2. From R2, there are still uncountably many lines are left. Many lines are left from x and also from y. So if we remove all these lines joining x to a2, x2, a1, x2, a3. Right? If we remove all this, we delete these lines, so there are infinitely many, uncountably many lines left from x and also from y. Right? So since there are uncountably many lines, so there must be some lines which intersect. Right? There must be parallel lines also, but there must be some lines which intersect each other. Right? So means there exists a line L1 from L1 through x, L1 through x, and L2 through y, such that they intersect at some point of R2 minus a. At some point, say P in R2 minus a. Right? So we have found there are uncountably lines. So there is a line, this L2, this is L1, and this is L2. This is not a line, but there exists a line. Okay. This line, suppose this line. So it intersects at P. So this means we have found a path which is the union of these two lines, L1 and L2. Not whole L1 and whole L2. This is the L1 and this is whole L2, right? So we have found a path from x to y, right, through this P, which lies entirely in R2 minus a. So R2 minus a is path connected, right? So this means this P determines the path from x to y. So we have found a path through this P, joining x and y in R2 minus a, right? So this means R2 minus a is path connected. Okay. So since this is time, I am not starting components. So I will discuss it in the next class. Okay. So now if you have any doubts in this session, we can ask. Shraddha, is everything fine?
Yes, ma'am, but difficult to understand. New topics are there in math.
Yes, you have to study. Uh, so
Ma'am, criteria of the exam I prepared to final exam?
which criteria?
But criteria not. It's
Which
about questions
which type of
which have.
question?
Uh,
That I cannot say because we don't prepare the questions. So we are here to help you to solve the assignments. So if you have any doubts, if you read, so there is 9 classes left, I think. So you read the topic, then if you have any doubts, you can ask. This is the starting.
okay.
You have to study now. This is the starting point. So don't you get demotivated right now. There is time. Okay, so just follow the class and the lectures, and the notes are available in the site, right? I have shared the
Okay.
class notes and video link, so you can prepare. Okay.
Okay, ma'am.
Okay. Okay, now I'll. Okay, so I am ending this class. Okay, good night.